almost macroscopic micrometer scales to atomic scales. We learned that transport goes from diffusive, ballistic to quantum. And when I was a grad student, it wasn't even clear what formalism you would use on describing this kind of structure. Physicists write down a Hamiltonian. They typically work in a law of equilibrium. And maybe they do sophisticated things with self-energies. But I'm an electrical engineer, not a physicist. My problem is I actually have contacts on my devices. They're out of equilibrium, very far from equilibrium. I shuttle electrons through. So this whole thing of dealing with equilibrium isn't even valid for me. Yet I have to do quantum mechanics, statistical mechanics out of equilibrium. So at that time, the non-equilibrium green function formalism was emerging. The cool thing is you can rederive the standard approaches of Boltzmann and drift diffusion. You have a unified model, and you can deal with a whole slew of devices in that same formalism. And we are doing that now. We look at quantum dots, we look at ultra-thin body transistors, nanowires, carbon nanotubes, graphene. Those might have been words that you heard, at least in the popular literature. And it took about 18 years of development of software to do that. And the perception is that to do that, it's incredibly expensive to compute. And it is. We actually run on the biggest supercomputers in the world. This is a scaling result on Jaguar. That's one of the softwares we built in my group. This code scales perfectly well to 220,000 processors. Generates a sustained petaflop of 1.44 petaflop on the largest machine we can do. We can do engineering now. We can do runs in an hour that would take 25 years to run on a single CPU, right? But running multiple things in an hour or half an hour now is engineering. You can actually run multiple scenarios, explore, not just hero runs. And so it's really engineering at the petascale. This is probably the first petascale engineering code. Most other codes I know are science codes customized to a certain particular question. Our code can address all of these different devices that I mentioned. All right, so the cool thing is last week we got an honorable mention in the Gordon Bell Prize. Unfortunately, the Japanese have a bigger machine by now, so we can't compete on that. Yes?
Sorry.
Okay. So what kind of problems can you solve? We study transistors. So you relevant, and it runs in the nanoHUB. Okay? This visualization is just a screenshot of something you can do on nanoHUB today. Everybody of your group, this group can log in, sign up, and run this. And it's a reasonably sophisticated visualization and simulation, and it's open to anybody. And it gives insight. We can actually, with the simulation, we can help experimentalists tune their devices, understand their devices, and even more, we can do metrology. We can figure out what they have built, because you can't really break these things apart all the time to figure out what you built. So this is real stuff. It's not Java applets you write for a particular class and you're done with it. It's really research code. It runs in the web. So obviously not everybody gets access to Jaguar, right? So they can't run all the highest end runs. But we put it in the nanoHUB, and we support 6 tools that are serving over 6,700 users with over 100,000 runs. On research software, I had no way of disseminating before about 10 years ago. But just one software isn't quite enough. You have to have a plethora of pieces of software. In fact, right now we have a system that operates over 220 pieces of software, and they all have these features of interactivity, overlaying data, exploring data, and asking what-if question. What happens if I make this gate longer? Or what happens if I replace these atom types by others? You can actually explore it interactively, at least on the results section. Some things run in seconds, some things runs in minutes, Others run for a couple of hours. All right, but these tools are not enough either. You really have to put in more. You have to put in courses that teach people on how to think about these problems. So we have over 55 complete nanoscale nanoscience courses on nanoHUB, and we have over 2,200 seminars, teaching materials, homework assignments, etc. on there. All right, so here's a new initiative. We're actually starting to do this online teaching to an open course where we allow anybody just to sign up to a set of lectures. Superior Data starts on this, on concepts on quantum transport. All right, so I'll give you a little bit of a video. Sorry, I have to. Can you turn on the sound on this, or?
Imagine a technology that helps you explore a new area of science.
All right, I'll just go through. So it's a science gateway. You can download things, but you can
And not only download resources,
you can browse seminars. They're interactive. They're basically voice
but learn from leading researchers online.
Like this. So in this form with Breeze,
Not with blurry videos, but through animated seminars where you can hear the speaker talk and clearly see his slides, where you can search for concepts and get right to the point. Imagine having fingertip access to simulation tools that are easy to launch. Tools with intuitive controls that are well documented. And results that are readily visualized.
You can have a visualization of a carbon nanotube. This graphical user interface looks very sophisticated.
And not just one
tool.
tool.
By an undergraduate who doesn't even know what a carbon nanotube is in 1 week. Okay? So it can be done. Different tools. Here's a resonant tunneling diode. Before there was a nanopore. This is a transmission. Here's a quantum dot. These are artificial atoms. You can look at the wave functions of these artificial atoms. So here's an S-like orbital, a P-like orbital. Different quantum dot tool that looks at absorption of gold particles. Here's a nanowire tool. This is a more heavy-duty computational tool. When it runs, the runs get actually disseminated into open science grid in this particular case. So it gets submitted here into Fermi grid and GLOW, etc. And it's transparent to the user. These users don't have a grid certificate. They don't even know what MPI is. They don't know what Condor is. Right? It's transparent to them. There's a question and answer forum. I'll talk a little bit about that. There's a reputation system that we're building. So that gives you an idea of what's sort of in the backbone of nanoHUB. And if you look at a map of users in September of last year, you can sort of say we keep people up at night. I mean, wherever there is light on the globe at night, we can have, in an integral sense, we have users. The growth is kind of staggering. If you think about nano as a tiny area, pun is intended, there's 19% of all .edu domains in the US, and there's about 7,050 that have nanoHUB users. And that includes your haircare.edu and all kinds of other small schools that are non-technical. All right, so you've seen the animation in my opener, but what we in a sense have is kind of like a matrix, right? There's no way of us, all these users telling us what they do. We actually have to begin to figure out what they do. So we created this matrix in a sense, and we need to look at it and study it. I can give you raw numbers, but those are kind of boring in a sense. I mean, we had, in the academic year 09-10, we had 8,600 users running 345,000 simulations. That's just some raw number. We know from self-registration we had 116 classes at 97 institutions, and we found 575 citations in the literature. But you have more questions than that, right? You like to know, is it a sustained use? Do they come back? What tools do they use? What intensity? What compute cycles does an individual consume? And I always get these questions. Are you research or education? What are you? Right? What are you providing? So let's look at this. From the back, it might be hard to see. It's basically on this axis here, horizontal is time and days. And each row is a user, and each speck is a particular activity on a particular day. And each color is a different tool. So I'm going to look backwards in history, starting from June of last year. And you'll see users show up slowly as they zoom by. You basically have this kind of matrix effect, which is kind of cute. But the point is, eventually you start to see some patterns, or you imagine some patterns to see. So here's a streak. Here's a streak right there, more, a chunk. Suddenly a big chunk of users showing up. So there's something there that's coordinated, and there's something there that seems to be rather uncoordinated. And we developed some algorithms that actually look into that data set and try to understand it. So here are some of the patterns where there's basically a cohort of people that comes once, say on a Tuesday, to do their homework. There's a cohort of people that behaves very systematically and comes throughout a whole semester, runs one tool. There's another cohort that looks at one tool, 2, 3, 4, 5, 6 different tools in certain patterns. These are classes. I can positively identify these classes. I actually have contact to these particular ones. I know who the teachers were. And they are sophomores and seniors, freshmen in chemistry, graduate students. And then there's other users that have no correlation whatsoever. They don't seem to fall into patterns. But I know from publication records that these are experimental researchers, and these are computational researchers. And then there's a bigger group here that I know nothing about. And these groups are not small. Like these groups up here, there's A, B, C, and D. We have 96 classes that behave like A. We have 5 classes that behave like B. We have C is 1, D, there's 41 classes that have patterns like these. Now those teachers I didn't talk to, right? I didn't validate them, right? I don't have that much time, and my assessment team is not that big to do all that. So you have to have sort of automated processes now, but we can now measure the classroom size. We can figure out what tools they use, right? Because it's a unique identifier what tool. We can classify those tools as educational tools or as proven educational tools. All right, so this myth that you can't use a research tool for education is sort of busted, right? Because here's a proof. This is not a hypothesis that might happen. We can now begin to measure the time. How long did this tool that might here be a research PhD thesis, how long did it take for that to show up in the classroom? Okay? And that time is, I think, 2 or 3 years on some of those tools. All right, so now this year we're over 3,000 students that behave in a coordinated way like that, in a systematic way that we can identify. All right, we can also measure the computational requirements of these people. So each of these classes, A through F here, I can now plot the number of number of runs they've done and the CPU time they consumed. And you can sort of see there's differences on how these individual students behave. Some of them use it very extensively, others don't. I can now think about provisioning of these computational resources. And on average, here's the sort of the white line where people sort of run 20, 30 runs that take a couple of minutes to run. But the spread is reasonable. I can now look at these guys that are uncoordinated, right? They don't have a certain pattern with each other. They consume a whole lot more cycles. The computational guys are here out in sort of turquoise. They're out on the fringe. The purple guys are the experimentalists, don't run as much. And these are the self-study users that I don't know much about. I can compare these. I can put them on the same chart. It turns out, so these computational guys, these researchers are running more and more extensively, on average, an order of magnitude more runs and more intensity. And these guys I know nothing about. They behave like these classroom users, but they're uncoordinated with each other. They just show, they learn just like classroom users do. All right, so myth number 1, you can't use research tools in education is busted, right? Here's a concrete proof with numbers. And the codes are too hard to install. Well, not really, because nobody installs any codes. I mean, who of you teachers has any privilege in your own classroom to install a piece of software? Nobody, right? You have to overcome that where they can just use it without installing anything. Us software guys say, well, yeah, no problem, you just install it. No, but the end user cannot. All right, so the next myth is, well, you can't use this for research. This might be good for education, right? Yeah, the simple stuff, you can teach some bits, but research you can't possibly do. So I started to dig out the citations in the scientific literature that cite tools on nanoHUB, or they cite nanoHUB themselves. So each dot here is a paper, and the colors mean something, so I spell it out for you. Here it's nano, right, in red. There's papers about cyber infrastructure out here. There's now papers that talk about how you use nanoHUB in education. Those are these guys. And a line between a dot is a common author. So that means we are forming social networks of authors that are outside of our core group, that is us here in the middle. The good thing is there's 56% of the papers are outside of us. So we're not just self-serving doing our own stuff, but the stuff is actually getting out. Some of it is connected to us, some of it is completely self-standing. So today we have over 1,400 authors with 719 publications that we can identify. Now, we can also go into these nano papers and actually read them and figure out, are there experimentalists in there? Is there experimental data in there? Turns out about 30% of these papers have experimental data in it. Finding if there's an experimentalist on there is a little bit harder, right? You really have to look for, we designed an experiment, we built it, we measured it, and we either used software to interpret the data or to design the experiment, right? So there's about 12% of the papers that fall into that category, which I claim is a success. It really means we are enabling others that are sitting on the outside, that are experimental workers, that use our research tools. So the myth that an experimentalist will never touch this is also busted. So then the next thing, after I show these kind of charts, they say, well, yeah, that's fine, but it can't be good research. So how do you quantify good research these days? You look at the H-index. So I presume you guys know what an H-index is, so I don't have to explain that, but basically you rank the citations of the papers you wrote, and if you have more than 6 papers that are cited more than 6 times, then your H-index is 6. So here's an example of a young faculty member, so he's doing well with 6 after 3 years of his PhD. Here's an example of an Academy of Member of Engineering. At the time, 2 years ago, his H-index was 37. So with some 500 papers, 30 to 100 secondary citations, you could ask yourself, if nanoHUB were a co-author on these papers, what would the H-index be? Right? Supposedly, if you're in business for n years, your H-index should be on average n. We were, at that time, in business for 8 years or so. So our H-index at that time was 27, and now it's 30. So that means not only can we support research, it actually is impactful research by whatever that means, right? It's H-index, we can agree or not agree, but it's at least one metric. All right, so what are these people doing? So here's a network. I can now home in, this is an older chart. I can home in on, say, a certain tool set. Like here's a tool, Shred, that is very popular in research. I can sort of home in on what people do. So here's an experimental group that is using it for real papers. I can dive into the papers. I can connect it. I can also look at their activity on nanoHUB and look at their downloads and their usage, and then when the papers show up. I can do something similar with computational guys. These guys here, I know this person actually personally, they build their own tools and they use it as a benchmark, right? So they download the software. They don't use it much on the web themselves, but they get access to the source. They compare their own methodologies and use it as a reference. Also a nice way of using it. There's a whole group of people that does that. We can also begin to connect their usage to their publication record, so we can start to think about relating usage to research more directly. So how do some of these tools look like? And typically, a research code looks sort of like this, right? You have a cruddy input deck that takes a mother to love it. And nobody really can use it. This is actually reasonably sophisticated. This is an industrial strength tool we got from Bell Labs. This is how they used to design their transistors. We added something on top that you can run this now many times on the web, and you can ask what if questions, what if you change these parameters. So that's already nicer. But we can do something more. We can take this tool engine and wrap an interface around it that is limited. It's not as general anymore as that beast of an engine, but this one can design transistors. A particular kind of transistor, but you don't need to read the manual on how to run this code. You don't need to know how to place the semicolon or anything anymore. You have a graphical user interface, and also this built by an undergraduate in an undergraduate program in the summer. We do this with the same engine for 6 different tools. We find 6,000 users use that. We still have also geeks that really want to have the engine, the full-fledged engine. But all of those are allowed to be on nanoHUB, and they're being fostered. But the key is really the user interface to make it work. We have created something we call tool-powered curricula, where you don't have to hunt and peck for all these different tools, but we can assemble a set of tools into a tool suite. And if you're teaching semiconductors, this is what you might want to use: crystals, band structure, PN junctions, and MOSFETs. And it's a one-stop shop for a faculty member and a student to have a set of tools with homework assignments in one package, rather than hunt and peck of the 2,000 content items we have. I mentioned user interfaces. So here is this tool Shred again that we used to have as an open source code and in this web form, sort of like what your bank has today still, right? You fill out a couple of numbers, you say go, you get a graph you can't do anything with. You can't say, what if I do this and overlap a graph, right? You can, but you have to download the data and massage it yourself. That's the system we called Punch that we had. And we retired that on that tool in mid-2005, and we replaced it by something that is interactive like this, what you've seen. You can look at data, and suddenly we see a little bit of growth. People seem to like it. What's even more astounding is that the number of downloads of the source code dropped rapidly. People really don't want to download source and install it. It's not a whole lot of fun, actually. So this is a proof that the interface is critically important, and that you have to think about it, and not just a computational guy that says, well, I can do it myself. That's fine. If you really want to enable others to use your stuff, you really have to think about how they would use it. All right. But that's not really new, right? So when these iPhones came out, everybody said, this is a piece of crud hardware, right? There's much better cameras. There's much better processors, right? These Microsoft phones are much more capable. Well, but if they're not usable, they're not really capable, right? So it's all in the usability. And people trade usability and capability all the time. And as scientists, we want to build tools that can do everything. But if you ask users, they don't want a tool that does everything. They want a tool that can do their task. And you can make their task much easier, much more powerful if you actually think about what their task is. All right. So the myth that you can't use somebody else's code to conduct research is busted. Experimentalists are using it. So next one is, why would I put something like that on the web, right? I can write my papers. There's no real incentive, and I'd have to hand over my code. So the normal web deployment looks like this, right? So you have a scientist or a graduate student that has a cool piece of software, and then you have a boss that says, you got to put that on the web. And maybe that boss is rich enough and has money enough or has a grant that says, okay, we really put this on the web, so you hire a web developer, and that web developer speaks Java, Perl, or PHP. This guy does not. I don't speak those languages, actually. And then slowly, in 2 or 3 years, you have a facsimile of this tool show up in a web form. In 2 or 3 years, this guy has either graduated or moved on in their science. In 2 or 3 years, this person has developed a code that is far superior to what he handed over 3 years ago here. That person will never, ever use this web tool. Who is the qualified person to judge whether there's good science in here? That person. He will never do it. There's no incentive. Plus, he got disowned. It's no longer his software. So we have a way to get rid of that. That whole process is gone. If you have a piece of software that runs in Linux with a user interface, you can put in a nanoHUB in less than 24 hours. Less than 24 hours if you have your own design tool that runs in a Linux environment with a user interface. We'll talk about the user interface in a minute. And of course, only academics are crazy enough that they say, we rewrite something to put it on the web, right? If you have a million-line vendor-like code, they're not going to rewrite it. So you have to have an architecture that basically transfers immediately. That is a speed up of roughly 100. If it takes you 2 years maybe to put something on the web, we replace that by a week, including building interfaces. So let me talk about building interfaces. Oh, sorry, one insertion. So how do we deploy it like this? If you have a tool that runs in Linux with a user interface, what happens is you go to nanoHUB, you run a tool, you request a tool, a virtual machine is being launched inside a physical machine. It runs an X11 type user interface. That user interface by remote desktop technology, VNC, gets piped to the user. So the user sees a fancy remote desktop, that's it. And if you do runs that are lightweight, they can do right here in that virtual machine. If they're heavier, they can be connected to a grid infrastructure. But they can be run on behalf of that user. That user is authenticated once, and after that, you don't have to hand over these identities, et cetera, to these grid infrastructures. They don't have to have a grid certificate. Now, if you have visualization, like line graphs are lightweight, you can do that in here. But if you do sophisticated stuff, we have a GPU cluster that sits in the backbone that gets the data, and then the user interacts actually remotely with a GPU cluster without even knowing what a GPU cluster is. But it's completely transparent. All right, so now the question is, my code doesn't have a graphical user interface. So how do you do that? So we built an infrastructure for building user interfaces and data management systems. It's actually the same thing. And what you do is you describe your interface by XML, which has a structured input to what your CRUD input deck is, and you have a translator. And it generates automatically a user interface, and it does it in any of the languages you speak. So you don't have to rewrite your code. So if your code is written in MATLAB or Fortran or C, you can wrap it with Rapture with APIs without touching your science code. In fact, this Padre industrial code that we got, we don't touch it. It's ancient Fortran. We don't have the expertise truly to touch the source. We have wrappers around it, and thousands of people use it. So that's the software piece, but how do you enable people to collaborate on these tools? So what I'm showing you here is a developer collaboration network. So each dot is actually a tool, and they're color-coded by their origin. So yellow here is Purdue, this is Illinois, this is Northwestern. The white ones, interestingly, are coming from the world. They're tools from the outside. They're not affiliated with us. And the lines between these tools are people. So there's multiple people working on these tools. So this is a collaboration network of tool builders. You can elevate that to the next level. So what's the impact of this group here? You can say, look, the yellow dot is now all the Purdue tools, and it's being used by 659 users at Illinois. Illinois creates tools, and it brings 212 users, gets 212 users from Purdue. The cool thing is, in an integral sense, 18,000 users at that time have used these tools, and the network benefits by use of 2,000 people using the external tools that came in. You can take another look at how important collaboration is in this chart. You can chart the number of collaborators a person has, so each dot is a person on a log-log scale, and the number of users they serve. So if you have a lot of collaborators, sort of up here, so 10, 20, you can touch 10,000 users. It's a whole lot better than writing a paper that's read by 4 or 5 on average. Okay? It's a different way of impact. It's a different way of enabling science and research. But it is impact. Speaking of this impact, is we have building incentive systems. So why would a faculty member put that stuff up? So here's Dragica Vasileska. She built that shred tool that I mentioned before. She built a lot of other tools. She's serving 11,000 users in an integral sense over the years. That's quite some impact. She uses these charts in an NSF proposal. She's not dreaming of eventually, maybe, possibly having an outreach program where she might eventually, possibly put something on the web that maybe, eventually, possibly is being used by someone. No, it's quantitative. Now we're writing books together, so that's sort of some self-advertisement. But here's another example. This is Sheikh Ahmed. He was actually Dragica's student, then he came to be my postdoc. And in his time at Purdue, he built some 8 tools, and he served some 6,000 users. He then went to Southern Illinois University, and suddenly usage at that place picked up dramatically. And he built nanoHUB into his existing curriculum. He built a new curriculum that didn't exist there, and he embedded it into the classroom, into his research, I'm sorry. And then he called me up after 2 years of being there. He said, they want to put me up for promotion. Can you write me a letter? I'm like, should gladly write you a letter, but it's pretty early. He got promoted with tenure after being there with 2 years. And his impact with and around nanoHUB was constituted as an element in that. We are building incentive systems for people to do that. That's a key element. We are an institution on iTunes U. It actually took a vice president of Apple to get us in there. They call us a nano app store, which is kind of a nice compliment. We draw a lot of users there each month. We are putting content into Wikipedia. We don't just want to do a link farm to nanoHUB, but actually make Wikipedia nicer and translate into other languages. Actually, people are doing that. Germans obviously know what a buckyball really looks like. So, but we are drawing some 4,000 visits monthly now that we started to more actively engage and disseminate on Wikipedia the content we have, because we have powerful content. We'll find a new way of managing that. So, we have an incentive system somewhat now that might entice people to put stuff on nanoHUB, and we no longer disown them. Okay? You don't have to hand over your code to somebody else and lose control. And I'll talk a little bit about the lose control in a second again when I talk about this CI operation. I hope by now I have you convinced that I don't have 9 FTEs per tool for those 220 tools of NSF funding, right? So obviously we're doing something radically different in its methodology to create tools and put them on the web. I'll talk a little bit about some of these scalability items. So in green, I'm showing you the number of tools as they grow. So we are at 220 right now. And blue, that's the number of developers that are working on these tools, nicely growing. What's in red is the tool versions, how the tools change. So we have over 1,200 changes in these tools, on these 220 tools now. We no longer disown the original owners. They stay connected. They improve their own tools. Okay? It's not something you throw on the web for those other guys, those poor people that are not as good as me. It stays engaged. There's a cool aspect to that. I'll talk in a minute. First of all, I'm going to talk about how do you manage that? Right? How do you manage the interaction of these 300 developers that might have demands, right? So what we actually built is a cyber infrastructure for developing tools that connect this tool developer to the end user. And it goes through stages. So if you have a tool that you want to get on nanoHUB, you register it, you create it, you upload it, we install it, you approve it, we publish it. Okay, there's a certain stage. It's like an inverse shopping process on Amazon, but you upload and you change rather than purchasing download. So it's a publishing system in a sense, and there's no emails flying back and forth. I told you a month ago I did this and you didn't react, right? Everybody's roles are defined. So if you're engaged, you know where the ball is and in what court. And we let you know. So we're waiting for you on something like review your own resource right now. Okay, it's been staged, you get to do a last review, sort of like galley-proofing your paper. All right, so here's an animation. each dot is a tool, and you sort of see them grow in time, and they go through stages. So the green tools are published, the blue ones are approved. And whenever you see a line shoot across, that's when there's a communication or an action being taken on our central site. This process of interacting with these developers here is done by one person on our central infrastructure. Okay? So we have put in place something that is scalable, that interacts with a lot of tools. And there, I mean, especially at the beginning of a semester, there's a whole lot of stuff going on, because I got to put my tool on the web, right? I'm teaching my class next week. I'm not sure I'm going to go to Christmas where it gets really quiet. I'll just skip forward. All right. There's another aspect to the server-side business. I talked about 190 tools actually in 3 years. No, this is on, okay, 5 years. 1,000 version updates. So if you're in the normal mode of science tools that you install on this thing or your cluster or wherever, let's assume you downloaded the whole nanoHUB software stack, including all the apps, 2 years ago. Right? So how up to date would it be? About only 30% of the tools would be up to date. Right? So you'd be installing and uploading a whole lot of times. And are you really going to do that when you use that for teaching or your own research? Are you really going to do that in an infrastructure that doesn't give you access to the backbone? Even in a year, we're down to about 60%. And of course, if you downloaded 2 years ago, you would miss that whole chunk up here. You miss the whole innovation piece on new tools. So what we have really is a server-side lifecycle management. Right? There's tools that are alive on the website, and you don't, as a client, have to upload anything or download anything. So how do you manage all these user interactions? You must be flooded by tickets, right? Flooded by problems. How do you deal with that? So we built a ticketing system ourselves that sort of works like this. It used to be that a user has a problem, right? And we have our central hub infrastructure, and they get tickets that might say, well, you know, I ran this transistor code and I put in these numbers and it didn't work. And our guys go like, transistors? I don't know anything about that science application, right? They're the wrong guys to answer that question. So they would have to reroute those to, by hand, right, to somebody that actually knows about this tool. It's sort of not very scalable, right? It's very labor intensive. So we're also being asked to, can you sort of identify tools you really care about? So we have our nodes like Purdue, Illinois, Caltech, not Caltech, University of California, and Northwestern. They have adopted some tools that they deem to be their core competence, and within 24 hours they want to answer tickets. And we route the tickets directly to them if they're science questions. If they're scientific questions, so we have a question and answer for them, the site leads get those and they can answer them. The core team only has to answer tickets when there's a systematic error, like my tool doesn't start. Right? That's a system error type thing. All right. So, and then there is a sort of a ticketing system that goes into your dashboard where a developer can see, oh, these are questions I have. These are new questions. I should go there and ask them. So it's integrated in their workflow rather than sort of exterior to, oh, yet another email. All right. So we built a strategy for community-supported tools as well as NCN core-supported tools. There's another aspect that is, we had a lot of questions on these unsupported tools, but not a whole lot of answers. Right? You need to have some sort of incentives to answer those. So you can earn nanos now on nanoHUB. Right now you can't do a whole lot with them, but get some t-shirts or cups. But maybe down the line you get more storage, you get faster computing. So we built a virtual economy on maybe fostering collaboration, fostering participation. After we did this, we basically 3 to 8 times fold increased the activity on the question and answer forum. People actually like to earn some nanos. These nanos may not be very meaningful by now, but it did foster contributions. I'm also working on trying to foster more collaborations in order to advance the scalability. I'm working with Anja Savikin. She's in the audience here as well. She's an economist, right? So can we study certain characteristics of users that some of them are anonymous, some of them are not? Can we give them incentives to collaborate? And we really have three types of contributions. We have tools and educational content, and that's not easy, right? That doesn't take 10 minutes and clicking on something, right? That's a pretty dedicated task. But rating of content is pretty easy, especially after you used it, but still we find people don't do it. They just consume and they don't give you feedback, right? It's almost you have to twist their arm, tell me, well, was it any good or not? And there's a question and answer forum where we also see that questions aren't as rapidly answered or answered at all. So we did a study that is really a field experiment where we contacted other users, and we had some findings that really people look for private benefits. If you talk to them about it'll be better for you if you do this, rather than it'll be better for the community, who cares? Seems to be the answer. People are driven by their private interest, and that's what that study effectively said, and Anya is in the audience there. If you want to talk to her about this, you can. Here's another old slide, 2006. People asked, so can you possibly provide these services, right? And I started to plot time per run and number of users, and basically there was an exponential line saying, only if you run fast will you have a lot of users. Seems intuitive, right? And we said, we really start down here and we will work up there. This is actually original slide. This is where we were in 2009. Basically, that exponential fall-off has vanished. That means we have created user interfaces that make it worthwhile to wait for a while. Okay? So that's the positive message, I think. So people talk about HPC, high-performance computing, and how critical that is. My key element is supercomputers, by far, are still utterly useless for engineers unless you really make them available and transparent. And that's what we do. We make them available where needed and enable people to use it where needed. So we've built an infrastructure that supposedly a university couldn't build, and that's one of the myths to overcome. The codes don't get out of date. In fact, they get updated all the time. And so far, we haven't run out of cycles. All right. Bit of industry impact. I can look at my citation maps. 8.7% of these papers have authors from industry. I think that's pretty good. When I was in industry, I wasn't paid for writing papers. I was paid for something else. So even in a research type environment. So actually, I consider this a pretty high number. I talked about this Omen and Nemo code. It's being now used and transferred into Intel. They're starting to use it in their research groups. There's actually a really cool tool. It's a virtual STM instrument. So that's a tip scanning over surfaces. That is being used by all three AFM manufacturers in the US to advance their instruments, to test their own tools. And there's a quote that states as much. There's now initiatives to take these tools and not only virtually measure them, but also virtually build what a carbon nanotube might look like on the surface, and combining instruments like that. So it leads to new funding. So I'm sort of winding down now in terms of the achievements or what was important. We demonstrate knowledge transfer, knowledge generation, we have economic impact, and we work on professional development. Those are the things we had set out to do. And so you can ask yourself, so what do some of the users say? And I looked at some top 75 words of 159 notable quotes, and 527 content reviews. And people are looking at simulation and tool presentations. They're using them. Some of them think it's excellent. They like it. It's good. Lectures. So those are some of the words, top 75 words. This is done with Wordle. I'm not sure if you're familiar with that. So what we have is Mike Rocco calls it the world's largest nanotechnology user facility. In an annual sense, we have 180,000 lecture users, 11,000 simulation users, 300 simulation developers, 830 lecturers that contributed to nanoHUB. So it's a community that's forming. I've shown you systematic use in research, systematic use in education. So in a sense, you have a science gateway's dream, right? So the question is, why aren't there many more like that? What's so hard? And it's really so hard because there's worlds in between research and the real world. And in investment, you call that the valley of death. And you kind of have to come over this valley of death, and you have to have a prescription to do that, and some methodology and processes. So I'm going to try to give you 7 criteria for that. So one is, sounds like duh, you got to have stuff the world wants. You got to have a lot of stuff the world wants. Much more than NSF will ever pay you to put on. You have to have leverage, lots of content. Okay, so if your proposal says, I will put one tool online, to me that's dead on arrival. It better be the one tool that's needed for the single tool for the cure of cancer, which is probably unlikely, right? It has to be a plethora of tools. The second one is more subtle. You have to have people that want to give stuff away. That's not as clear either, and finding those right people and engaging them is actually hard. The third part is, well, this is the incentives I mentioned. The third part is the technology. It's almost, in that sense, minor now. You've got to build that bridge. It takes about $1 million a year to just operate bare minimum nanoHUB, okay, just to keep it alive and up and running. That doesn't even touch the new stuff, right? The things we want to do to make it better. All right, so we built this hub infrastructure that underlays it. But you need a fourth thing. Faculty members are great, they're inventive, but they don't walk over this bridge. They have lots of stuff to do. Would you like more stuff to do? All right, so we have a process that we put people in place that carry stuff over the bridge. We call them site leads. You might call them consultants. Those are the people that polish the doorknobs on our campuses and find people that want to put stuff on there, engage them, help with the process, and they carry it over. Not the research piece. This is where we spend most of our money, in that tech transfer process. That's something NSF still has a hard time seeing, right? Where's the value in this? Well, the value is nobody's on this side can use it if it's not carried over. All right, so then you got to understand your stakeholders. I talked about the geeks, the operation piece, and the users, right? If you don't do that, you can't be successful. And you have to be open in your assessment. I think it's critical that you're actually really open with your numbers. You figure out what works, what doesn't work. I challenge anybody involved with the Science Gateway, put your stuff up there. Exceed. Put your stuff more open out there and tell us who uses it, for what, and what the impact is. I think that's an incentive to be built in the community. We do this study. We have a business model. Ours is academic funded, but if you want to drive this into industry, you have to have a real business model. So what's next? So we're building a mirror hub in South America. It's happening very soon. What I really want to do is really think items that are bigger. We spun out Hub Zero. There's some 30 hubs that use Hub Zero now. We have built a Hub Zero consortium. I really want to connect this to other initiatives. So Nano, we are engaged. There's been an announcement by Obama about manufacturing and the materials genome initiative. We do all kinds of briefings on this materials hub and the manufacturing hub. It was kind of cool. I was allowed to go to an event here with Obama where this was announced. A week later, some friend of mine sent me an email. Hey, you were in a presidential document. I'm like, oh, really? That's kind of cool. Which one? What is it? So here's this materials genome initiative. You go to page 5. You can really read that, right? So I make it large for you. nanoHUB supports the use of computational tools in nanotechnology research. Researchers can access state-of-the-art modeling and algorithm to collaborate. It's an exciting system that's a good example of a first step towards open innovation. So I hope that is being embraced in this materials genome initiative. We did create a manufacturing hub. We have a Midwest consortium now with companies like P&G, Lockheed Martin, John Deere, to enable something like this for small companies which do not use modeling and simulation today. So I see this as a federation of hubs that have different customers. DOE, DOD, global partners, industry hubs. I've shown you some of the success criteria, and we have to take serious steps. So I'm going to share something with you as we are preparing for the next 10 years of nanoHUB. Where I see this going is we all read our papers no longer in hard copy, right? We read them in our favorite electronic form. But we all know we can't be connected to the data that actually lies under here, or the tools that lies under here. What I want to build is an infrastructure that allows us to really elevate computational science to a real third leg of science that is reproducible, that allows people to really reproduce these data. And what you might have is you click on this graph and it brings you to the tool that generated this graph. Now here we now have a real incentive for people to put up their tools because they can actually tie it to their own publications. A tool would be a publication. It would be valued by a tenure committee. And you can explore the data, maybe copy it, put it in your own paper, insert it. And the interesting thing is we have metadata that is around that tool. Since we use Rapture, all of these tools have metadata around them on what machine they ran on, what the input parameters are, what the languages are, what the tool sets are. We don't have to negotiate, are we speaking Chinese, German, or English, right? What's the right ontology for these data? At least for the simulations we have already the right ontology. We can tackle the thing that everybody is not even tackling yet, which is how do you explore data like that once you settle for an ontology? So we can start to explore. There will be lots of papers, lots of data. Where do we explore it? We'll explore it on nanoHUB that has a data browser and a tool browser that allows people to compare their own data, upload their own and compare to experiment. So we'll do connections to more nano centers. Maybe we are the central repository of nano knowledge. But really I want to make computational nanoscience more reproducible and become the repository for data, enable rapid exploration, revolutionize education. So that's really sort of a big words. So here I'll thank you for your attention.
Great.
Thank you.
Great. We have most of the associate directors for NSF waiting in about 15 minutes. Unfortunately, we've got a context switch to do here. We don't have time for questions, but Gerhard will be around for at least part of the afternoon and over the breaks and so forth. As Gerhard said, there are hundreds of so-called portals and collaboratories, science gateways around. There's none, and I can say this, I think, with quite a bit of authority, that has had profound impact, as you've seen, and certainly none for which the impact has been quantified in the way that he's done this. So I underscore that this middleware, this nanoHUB middleware, is being used now increasingly widely for other fields and disciplines. And if you have any interest in exploring it in your particular work, let us know, and we'll play a brokering role there. Sure. I don't know.
They're not online.
Go ahead and you answer that.
So are the slides online? I gladly put them online since the last vision piece, because we are competing right now for 10 more years. So I can give you all those slides to you personally, that's fine. I don't want them online quite yet. In a month, I don't care, we'll have the proposal written and handed in. But
yeah, and we will be embargoing the video version of this for a month or so until he gets the proposal submitted. So thanks again. That was a terrific talk. If we could have another one. Okay, Sharon. Okay, now I'm going to turn the microphone over to Sharon, and we really need your cooperation in expediting this shift to lunch, coming back to lunch, and then initiating the hangout with the NSF directors.
I just have some quick instructions. We are in a time crunch, so the instructions are: 1, grab lunch in atrium 2 left when you exit from the doors here. Special food requests are going to be separated out. There'll be a sign. Sufficient lunches for walk-ins are available, so if you're a walk-in, you can take lunch. You need to be back here by noon. And then unrelated, yeah, the sooner the better. Unrelated, if you're from outside U of M, Wi-Fi access is now available. Ask at the registration desk. And that's it.
Ready, set, go.
We test this one more time. Your sound didn't come out. Did your sound come out?